pin diagram of IC741, which is an operational amplifier. As we see, the first pin is offset null, second pin is the inverting terminal of the amplifier, third pin is the non-inverting terminal of the amplifier, fourth pin is negative power supply, which is minus 15 volts, fifth pin is again offset null, sixth pin is the output of the amplifier, seventh pin is the positive power supply, which is plus 15 volts, and eighth pin is not connected. Now let us see how to select the resistors and capacitors values in order to set our required cutoff frequency. Cutoff frequency is given by the equation F is equal to 1 upon 2 pi RC. So accordingly, if we choose one of the parameter amongst R or C, we can easily get the value which we require for the cutoff frequency. And in second order Butterworth filter, the relation between the feedback resistance and the input resistance is given by Rf is equal to 0.586 times R1. So accordingly, we can choose the values of Rf and R1. Having known about the pin diagram of IC741, let us have a look on circuit diagram of second order high pass Butterworth filter. It consists of an op-amp, two RC networks connected to the non-inverting terminal of the op-amp, an input resistance, feedback resistance connected to the inverting terminal of the op-amp, a load resistance connected at the output. The input signal is given at the capacitor of the second RC network. Now, quickly make the connections on the breadboard as seen in the circuit diagram. This is the first RC network, and we are going to the second RC network. The input resistance, feedback resistance, a load resistance, in order to enable the operational amplifier, we need to provide 30 volt power supply in the form of plus 15 volts and minus 15 volts. And now we are connecting the input using the crocodile wires connected to the function generator, and using the CRO we can see the output of our circuit by connecting it through a crocodile wire. This is our final circuit, and now we are ready to check the output of the circuit. As this is a high pass filter, output is expected to appear in the frequency domain near to the cutoff frequency of the circuit design. Let us vary the frequency and observe the output on the CRO. Our cutoff frequency is 15.9 kHz. So let us start varying the frequency using function generator. So it is 10 Hz and we observe that the output is 0. Next 100 Hz, still we don't observe any output. Let us go to kilohertz now. Now it's 10 kilohertz and we observe some amount of output on the CRO. So let us try to change its time domain and see the output more clearly. So this is frequency. Okay. Yes. Perfect. Now we can see that at 10 kilohertz range, some output is appearing on the CRO. Let us try to increase it and find what difference it makes at higher frequencies. So we have increased it to 100 kilohertz and we find that the output has increased in its magnitude. Magnitude in this sense, its amplitude has increased than the original one. It means that as it is a high pass filter, the output starts to appear in the frequency domain near to the cutoff frequency, and it appeared in the frequency range of 10 kilohertz, and as we increase the frequency, the output magnitude has increased and it is increasing to a certain level. After increasing to a certain level, it should continue to be constant in that particular level ideally. But as the CRO doesn't support the frequencies greater than kilohertz, that is in megahertz, we are not able to see a constant value of the output waveform. But ideally, it need to be constant after increasing to a certain value. Finally, we are left with visualization of the frequency response of our filter. Let us use a spectrum analyzer and observe the frequency response. Let us set the starting frequency near to our cutoff frequency and observe the response curve by increasing the frequency. As we can see, the response curve started gaining some value when it had surpassed the cutoff frequency, and it became constant further. And this constant value is observed to remain constant for a larger time.